Okay, before we begin, can you guys please confirm that you can hear me clearly, you can see the screen, and you can see me? You guys can't talk. Sorry. Let me just open the chat. Okay, perfect. Okay, sorry, I'm gonna start off by greeting because I think I forgot to greet the previous two classes. So, Assalamu alaikum and good morning, everyone. Welcome back to grade 11 physics by Inspired Teens. In today's lesson, we'll be continuing with mechanics, Newton's gravitational law. Okay, and we'll try and squeeze in an equilibrium example. Okay, so just a reminder, if you guys do have any questions, please feel free to leave them in the chat, in the Q&A, the YouTube chat. Another reminder, the document of the work that we do will be uploaded to the Google Drive, and the link for the Google Drive can be found in the group description on WhatsApp. Okay. Okay, cool. Sorry for being a bit late. You know how it goes. But yeah, how is everyone doing? Since I've been so work focused that I didn't even ask how is anyone doing in the previous two lessons. So I'm gonna ask you guys, how is everyone doing on this lovely Sunday morning where I am absolutely ruining it with physics? I hope you guys are doing well and that school is treating you guys well. No? Anyone? Nobody? Nobody's doing well? It's fine. Well, I'm doing well. Thanks for asking. Okay, so let's start, right? Let's so last week what we ended on was we did a Newton's first law and we did a Newton's second law, all integrated in one question, right? We had learned some really important rules. We didn't get to like an equilibrium question number one, and number two, maybe like such a complicated question. We didn't do like slightly tricky examples. However, we'll come back to them at some point, and we are thinking of hosting an extra lesson for you guys. So maybe we might do it in that extra lesson. Tired? Okay, that makes sense. I'm tired too. Okay, so nevertheless, let's continue, right? So we're going to learn about Newton's third law of motion. We're going to do some questions with regards to Newton's third law. Okay, so let's do some theory. Newton's third law. Can you guys see my screen or is it frozen? I think it might be frozen. Let me just reshare. Okay, I think that's better. It's been having some issues today. Okay, Newton's third law of motion, okay, states that when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. There's another similar definition. Every particle in the universe attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, that's more of a examinable definition. I need to make note of it for the examination guidelines. I'm going to put it in the Google Drive so that you guys can utilize it for your exam definitions. Okay. But yes, so basically Newton's third law, I think we all know by now, is that if one object exerts a force on another object, okay, both objects basically exert a force on each other, okay, irrespective of who exerted the force. And it is equal in magnitude, but opposite in direction. For example, when you punch a wall, okay, when you punch a wall, it's like the wall punches you back, okay, because the exact same force that you're going to punch the wall with is the exact same force that the wall exerts on your hand when you punch the wall, okay. That's why I don't recommend anyone to really punch a wall. But yes, okay, it's just opposite in direction, okay. So as we can see, as depicted by this, that the force on A on B, okay, the force that A exerts on B, any object A exerts on object B, is equal to the negative force that B exerts on A. Okay, so they're equal, but just one is negative. Okay, that's what we need to note. And B, Newton's third law describes action, reaction, force pairs. These are forces on different objects, cannot be added or subtracted. Okay, let's have a look at the formula. Okay, one of the main formulas. Should we do that or should we look at theory? Let's look at some theory maybe first. So a uniform sphere of matter attracts a body that is outside the shell as all the sphere's mass was concentrated at its center. Thus, the distance is determined between the centers of two bodies. Okay, so basically what this is explaining is that when in this section, when we calculate the force, okay, between two objects in the universe, we consider the distance between them, but not the distance between their surfaces, the distance between their centers. Okay, that's basically what this is describing. That's important to note. Not the distance between their surfaces, the distance between their centers. Okay, so as you can see, it says, note the radius of the Earth is added to the distance between the Earth and the Moon. Note the radius of object on the Earth is negligibly small. So basically, if you want to consider the distance between the Moon and the Earth, okay, you would consider the distance between their centers. Okay, so remember, you can have the distance between them. That's fine. Okay, but you have to also consider their radii. Okay, so we talk about the radius of the Earth. We call it RE, as well as the radius of the Moon. Okay, we call it R Moon, I guess. We call this R Earth. Okay, to consider the total distance, okay, we consider obviously the distance between their surfaces, but we have to add the radius of the Earth and the radius of the Moon, if we're considering the distance between the Moon and the Earth, right? And also, what was I going to say? I have no idea. Okay, so yes, that's important. Okay, basically just because we are considering the distance between their centers, all right? However, when we're working with a person or an object, if we have to have a little rock, okay, on the surface of the Earth, if we want to calculate the magnitude of force that the Earth exerts on this man or the man exerts on the Earth, okay, we just have to consider the distance between the center of the Earth and the surface of the Earth, because the person is on the surface of the planet, or if it's Earth, then it's Earth. So you just consider RE, the radius of Earth. Same applies if there's an object on the Earth, right? If you want to calculate the magnitude of force between the object and Earth, you're just going to calculate the distance between them is the distance between the surface and the center, because the object is on the surface. Okay, maybe it will make more sense when we do an actual example. Let's talk about the formulas. Okay, so the first formula we're going to learn is F is equal to G times M1 times M2 over R squared. Now, this is a force. Okay, it is a force that two objects exert on each other. Okay, what you need to understand with this force is on Earth, this force is Fg. On Earth, this force is Fg. Okay, because remember this force, just say, for example, we're calculating the force that two planets exert on each other. Okay, what you would do is it's the force that two planets exert on each other. But now what if we're using the object in Earth? It's the force that an object on the surface of Earth exerts on Earth, or the force that Earth exerts on that object. That would be this F. And on Earth, for any object, okay, object or person, right? An object on Earth, let's do this. Okay, this is Fg. That's important to note. So literally the Fg that we use in Newton's first law and second law, Fg, like m times g, that is what we're talking about, if it's an object on Earth. So all of this is basically equal to mg. Okay, because when we consider on Earth, okay, again, that force is Fg. Okay, hope that makes sense. G is a constant. Okay, here's all the things here. Okay, but anyway, G is a constant, right? M is the mass of the first object. M1 is the mass of the first object you're dealing with. M2 is the mass of the second object you're dealing with. And R is the distance between their centers. So I'm not writing anything because it's all here. Okay, so this F is the force of attraction between two objects. Okay, then we have G is universal constant, gravitational constant, which is a constant, 6.67 times 10 to the negative 11. M is the mass of the objects in kg. So if we're dealing with the Earth, the mass of the Earth, right? If we're dealing with an object on Earth, the mass of the Earth and the object, right? Then R, very importantly, is not the distance between them. It's the distance between their centers squared. Okay, we squared in the denominator. Now let's talk about this, right? This is another formula, which maybe many of you don't use. In this case, we need to understand that this here is G, and it is gravitational acceleration. Gravitational acceleration. Okay, and different planets have different gravitational accelerations. It's basically the acceleration due to gravity. So of course, different planets have different gravities. So therefore it's different. However, on Earth, we know that it's approximately 9.8 meters per second to the negative 2, right? This is on Earth. All right, so that we need to know that this is gravitational acceleration. This is G, the same G that's in mg. That's the same G. Okay, cool. Then the rest are the same. So G, big G, is the gravitational constant. M is a mass. Okay, it is a mass. M is a mass, but M is generally the mass of the planet. Okay, because this object, this formula uses the gravitational acceleration on a planet to calculate, or you equate it to, the way you can calculate the gravitational acceleration on the planet is you take G, the constant, multiplied by the mass of that planet, and you divide it by planet's radius, basically. So this is mass of planet. Okay, and this is a radius of planet. Okay, radius, which is this one. Okay, so this is another formula which we can use. Okay, you don't have to shy away from it. I'll be honest, we mainly do use the first one, but the second one is definitely possible to use and you need to understand it. Okay, so here's a little thingy that says know the difference, G versus G, right? We have small g and big G. 1 second, sorry. Okay, so know the difference. The small g represents gravitational acceleration, which, like you said, is 9.8 on Earth. It's the acceleration due to gravity on a specific planet. Big G is the universal gravitational constant. It's the proportionality constant which applies everywhere in the universe. That's for some genius that calculated it to worry about. We just know that it's a constant and we get it from our formula sheet. Okay, small g, on the other hand, that is gravitational acceleration. It's different on each planet, and on Earth, it's 9.8. Okay, cool. Let's talk about mass versus weight. Let's do this. Let's use blue and green. Let's talk about mass versus weight. So mass, which is in kg, is a scalar quantity of matter which remains constant everywhere in the universe. Okay. However, weight, okay, is the gravitational force. Weight is the gravitational force the Earth exerts on any object. Weight differs from planet to planet. For example, Fg is equal to mg. Weight is a vector quantity. Okay, let me explain that simply. Okay, that might blind you, to be honest. But basically, you know, when we have Fg is equal to mg, right? This is referred to as weight. weight is actually a force in newtons that basically you exert on the earth. Everybody exerts on the earth if you have a certain mass, right? And then this is the mass. This is the mass that we using in kilograms. Okay, so technically when you ask someone how much do you weigh, that's an incorrect thing to say. You should technically be asking them what is your mass, because if you ask them how much they weigh and they weigh 60, sorry, if you ask them how much they weigh and their mass is 60 kilograms, you're going to have to multiply that by 9,8, and that would give you the actual weight, which is not great. The next time someone asks you how much they weigh, you can say 588 newtons. Okay, technically the correct term is mass. Okay, but it doesn't matter. And of course, this is gravitational acceleration. So do I write it? Yeah, sure, why not? Gravitational acceleration. Cool. Okay, so just remember that this G is used here. Okay, and then remember that this F could be Fg because this is the force that two objects are exerting each other in the universe. And if the object happens to be on Earth, then the force that that object exerts on Earth would be considered as Fg. Okay, or any planet for that matter, provided you have the correct G for that planet. Okay, let's move on to some calculations. We're going to start off with those ratio calculations that come in multiple choice, and I'm going to show you how easy they are to calculate. So it says two objects with mass m1 and m2 are a distance of r apart and experience a force F. How would this be affected? How would this force be affected if? So firstly, let's consider this. They are basically giving you the formula because they're saying that two objects, m1 and m2, are a distance r apart and have the force F. So if I had to calculate their force, I would equate this to G, which is a constant, time the mass, m1, which is the mass of the first one, m2, which is the mass of the second one, and then r, I would square it at the bottom. R is the distance between their centers, and this should give me F. So they're basically telling us the formula. Okay, then they say one mass is doubled. One mass is doubled, and the distance between their masses, okay, let's just say distance is halved. So they are taking one of the masses and they are halving it. So this is the easiest approach, okay? So I'm going to show you the first way, which is basically you substitute each thing with their new change. So if one of the masses is doubled, I'm going to now have the new F equal to G, okay? G times, let's double the first mass, 2 times M1, okay? Times M2 divided by, just give me 1 second, let me mute. I'll be back shortly. Yeah, I really meant shortly, I'm back. Okay, so they say, well, one mass is doubled and the distance between them is half. So the original radius was R, and now the new R is going to be half R. Okay, I'm just showing you this way. The other way is easier in case you want to use this way, right? So in this case, now what I need to do is I need to try and represent it in terms of the first one, because I know that this is F. So I need to get the new force in terms of F. So what I do is I bring all my changes, numerical changes, to the front. So I'll bring the 2 to the front, okay? And then I'm left with G times M1 times M2 divided by, now if I square a half R, okay? For those of you in maths, I don't know if we've done exponents in grade 11. I think we have. But basically, you have to distribute this square. I think we did like yesterday. I think you have to distribute this square to each term. So you're going to square a half. When you square a half, you get 1/4. When you square R, you get R squared. No need for brackets. So it becomes a quarter R squared. So this becomes a quarter R squared. Okay, so if you notice, we have our variables in front, and on this side, we actually have this entire thing here. So the value of this is F, the value of the highlight is F. And then we can simplify the numbers. So when we simplify the numbers, it's basically 2 over a quarter, which becomes 2 times 4, which is 8. So it becomes 8 times F. Let me confirm it. Can I see the question? Sure. Okay, let's do this actually. Let's write it as 2 over 1 over 4 times G times M1 times M2 divided by R squared. That gives you 8. And this entire thing is F. So 8 times F. So how would it affect? They ask, how would the force be affected? It would be multiplied by 8. Okay, normally it's like a multiple choice question. Okay, so I'm going to show you the easier way to do it. So what you want to do is your original F, you're going to replace everything with 1. So G is 1, M1 is 1, M2 is 1, and then you get 1 squared at the bottom. Okay, then we consider one of the masses is doubled. Okay, so now this is to calculate new F. Okay, so one of the masses is doubled. So how do you double 1? You say 1 times 2, which is 2. So 1, because G doesn't change, times 2 times 1. Only one of the masses changed. Then they say the masses, sorry, the distance between them is halved. So you take a half and you square it. Please use brackets. And when you do this, you get the new F as 8. And that tells you that the new F is actually 8 times the old F. So it's 8F. Let's do it for the second example. They say both masses as well as the distance is doubled. Okay, so remember the original one was F is equal to M1 times M2. Sorry, I forgot about G. G times M1 times M2 divided by R squared. So if I double both the masses, what did I say? Substitute everything with 1. So 1 times 1 times 1 divided by 1 squared. And then to get the new F, I make the changes. So obviously G doesn't change, so it remains at 1. 2 masses are doubled. So 2 times 2 divided by the distance is also doubled. So it becomes 2R. So just times 2. And I square that. This simplifies to 4 over 4, which is equal to 1. So the new F, okay, is actually equal to the just F, 1 times F, which is F. Okay, hope that makes sense. Okay, are you guys fine? Normally you guys are the least quiet class, but today you guys are quiet. That's a bit concerning. Okay, hope that makes sense. So that's how you calculate them, right? Do not make it complicated. For each example, you can try numerous past papers. This method will work. Alternatively, if you prefer, you can use the first method, which is basically the same thing. Okay, just representing it in terms of variables. Okay, cool. Let's move on. Let's talk about this question here. Okay, so consider a satellite with mass. Let me get my notes. Where's my notes? I don't think I have my notes, but it's fine. Just we have a memo. Newtons. No problem. You're welcome. Doesn't G have a value? Yes, but I'm not giving G a value. I'm just replacing G with 1 because it remains constant. Doesn't change. That's the method, is to replace everything with 1 and then make the changes accordingly. If it doesn't change, you leave it as 1. It's not going to affect F. Let's look at this question. It says, consider a satellite with mass 1,200 kg orbiting Earth. The distance between the centers of the satellite and the surface of the Earth is 36 1,000 kilometers. State Newton's universal law, universal gravitational law in words. Every body in the universe attracts every other body in the universe with a force that is equal in magnitude but opposite in direction. It is directly proportional. Okay, you guys have definitions, right? I'm not a definition person, but yeah, it is a force that is directly proportional to the product of its masses and inversely proportional to the square of the distance between their centers, right? I hope you're not writing anything down. Formulas, again, you're going to find in your examination guidelines, which I am going to make a note today to put them up for those of you who don't have them. I suspect that some of you do have them and your teachers may have even printed them for you. Okay, so, right, calculate the magnitude of force that the Earth exerts on the satellite, F. I just want to note, they tell you magnitude, number one. Number two, we have a satellite that is orbiting around Earth, okay? Since it's orbiting around Earth, okay, they are in the universe, they exert forces on each other. The Earth exerts a force on the satellite, and the satellite exerts a force onto the Earth. Okay, always in this section, it's always attractive forces. Okay, so they both exert a force on one another, and they both exert the exact same magnitude of force on one another. So if, for example, the Earth had to exert 5 newtons onto the satellite would also exert 5 newtons, but negative 5 newtons onto the Earth, just opposite in direction. Equal in magnitude, opposite in direction. Okay, so one thing to note is that the satellite with mass 1,200 kilograms. Okay, the distance between the center. So they are giving the distance between the center of the satellite. Let's draw a little diagram, okay? Here we have our little satellite dish. They have given us this distance. They tell us that we don't have to worry because they gave us the distance between the center of the satellite. They told us it's 36,000 kilometers, which is in the perfect SI unit that we need. Okay, so that's what we have so far. Let's write out our equation because we know that we need to calculate F, which is the force between the two objects, which one is Earth and one is the satellite. So F is equal to, we write out our formula G, which is a constant, M1, M2 divided by R squared. Remember, R is the distance between their centers. So G is a constant, 6,63 times 10 to the negative 11. I multiply that by. Now, let's consider mass 1. Mass 1, I'm going to say mass 1 is the object of the Earth. Sorry, the mass of the Earth. M2, mass 2, is the mass of the object. Make sense? The mass of the satellite. So M1, the mass of the Earth, we can actually get from the formula sheet. The mass of the Earth and the radius of the Earth are given in the formula sheet. They're given in the formula sheet, right? In the back of your paper. So the mass of the Earth, I'm going to say from the formula sheet is 5,98 times 10 to the 24. It's given in kilograms. That's one heavy object. Okay, so remember, this is the mass of Earth. Okay, this is G, which is constant. Okay, now we need to do the second mass, which is the mass of the object. The mass of the object was given as 1,200 kgs. Well, I'm saying object, I mean the satellite. 1,200 kgs. Please do note that this is the mass of object. Okay. Now, at the bottom, we need to have the radius and we need to square it. Not the radius, sorry. We need to have the distance. Yes, you are correct. 6.67. 6.63 is Planck's constant. Thank you for that. Okay. So we need to have at the bottom, not the radius, not just any distance. We need to have the distance between the centers of each object. That's what we need to have at the bottom. Currently, if we look at our little diagram, again, nothing is stopping you in the exam from creating a diagram like this for you to understand the question better. Okay, please, I encourage you to do something like this, just so that you can visualize it. Many of us are visual learners, so you can visualize it and it might help you to understand better. Okay, so now I need the distance between their centers. Currently, I don't have the distance between the centers because I'm a good person and I read the question carefully and I see that the question told me the distance between the center of the satellite, but the surface of the Earth, the surface. So if I want to know that distance combined with, if I want to get the entire distance, so I need to get the distance from the center of the satellite to the center of the Earth as well. I need to include this distance, which is actually the radius of the Earth. So to the 36,000 kilometers, I need to add the radius of the Earth. Why? Because I need the distance between the centers of these two objects. The radius of the Earth, the distance, the radius of the Earth, the distance of the radius of the Earth in kilometers is given in the formula sheet. It's given as 6,38 times 10 to the 6 kilometers. Please, this drawing is not to scale. Okay. But yes, that's the radius of the Earth. Okay, so I need to include that. So how do I go ahead and include that? So the distance between the centers is going to be the combination of 36,000 kilometers plus the radius of the Earth, which is 6,38 times 10 to the 6. Okay, so now this, yes, that is the distance between the centers, and that distance I need to then square it. Don't forget to square it. So that's very, very important. Okay, that's us understanding how this formula works. Okay, when I do this calculation, I get the force that what they asked. I'll tell you in a second. I don't have the answer, so let me actually do it. You guys can do it and check if it's correct. 6.67 times 10 to the negative 11. I'm getting a force of 11,627 newtons. Okay, just so isn't it radius supposed to be in meters? No, it's not supposed to be in meters. Let me double check the formula. But no, it's not supposed to be in meters. It is yes, you are correct. It is in meters. The SI unit for this is in meters. Okay. Thank you for that. Okay. Sorry, people. The SI unit for this is meters. We have it here. Okay, if you need to revise it, it's all here. I don't know. This remove moment, I might get rid of it, but yeah, it's here. SI unit is in meters. Thank you so much for that. Kilograms and then newtons. Okay, so we're not using kilometers, we are using meters. So we actually need to convert. This answer is incorrect. we need to convert this guy to meters. So this is correct because this is given in meters. In the formula sheet, the radius, they're all given in SI units. So the radius is actually given in meters. Okay. However, this guy we need to convert to meters, and I'm going to convert it here. It's going to be, so you can just multiply it by 10 to the 3 to convert it to meters. Okay. So in that case, what I can do is, I knew I needed more space. Okay. I can write this as 36,000 times 10 to the 3. Okay, that converts it to meters. So 36,000 times 10 to the 3 plus 6,38 times 10 to the 6. That whole entire thing squared should give us an answer of times 10 to the 3 new. Should give us an answer of, somebody who did the calculation, double check with me that this is correct. This seems more correct. 266,59 newtons. Okay, this is the force that number one. They asked for the magnitude of force that the Earth exerts on the satellite. This is the force that the Earth exerts on the satellite, and it is also the force that the satellite exerts on the Earth. Same magnitude. Okay, let's move on. 2.2.3. How will the force that the satellite exerts on the Earth compared to question 2.2 write only greater than, less than, or equal to? Okay, so 2.2.2 tells us the force that the Earth exerts on the satellite. 2.2.3 asks, how will the force that the satellite exerts on the Earth compared to that answer? Guys, tell me, what do you think? Is it greater than, less than, or equal to? Correct. Okay, equal to, right? Sometimes in other sections, they might say give the relevant law or the relevant Newton's law that explains this. You will say Newton's third law or Newton's universal gravitational law. Okay, so yes, indeed, it is equal to. Very good. Okay, I hope that makes sense. Let's do our next question. Okay, so what we're going to do is this question. I'm not going to do the entire thing because I think it's the same concept, but okay, let's not push to do equilibrium. We can always do equilibrium next week. Sorry, I know you guys are in a rush, but I really don't want to rush. It's just because we started late. Okay, so the Earth exerts a force of 1,842 newtons to keep a satellite of mass 200 kilograms in orbit around the Earth, as shown in the diagram below. The Earth exerts a force of 1,842 newtons to keep a satellite of mass 200 kg in orbit around the Earth, as shown in the diagram below. Okay, remember it's an attractive force, so that's why they phrase it that way. Calculate the distance above the Earth's surface at which the satellite orbits the Earth. Okay, so here we'll be dealing with F. So our first step is to write out our F formula and fill in what we know. Now, it's a very similar question to the one above, where we have the Earth. Okay, I'm going to ignore the satellite. I'm going to say the satellite, my satellite is somewhere here. Okay. And the distance between the surface and the satellite is unknown. Remember, then there's that additional distance from the radius to the surface. Radius, surface to satellite. So it's Q, but don't mind it. So calculate the distance above the Earth's surface at which the satellite orbits. That's actually what they want. They want this black line, which I'm going to call X. They want the distance above the Earth's surface where the satellite can be found. Okay, so in this case, I'm going to substitute values that I know. Okay, so firstly, G, I always know. It's 6,63 times 10 to the -11, mass 1, so the mass of the Earth, right, which is given in kg, kg is the SI unit, 5,98 times 10 to the 24. Mass 2 is also given. Mass 2 is the mass of the satellite, which is 200 kilograms. Okay, and I divide it by, remember R is not radius. Okay, sometimes we use D. Okay, this is the, sorry, 6,67, correct. Okay, this is R is the distance, importantly, is the distance between the centers of each object, which we don't have, right? We know actually that the radius of the Earth, right? Radius of Earth is always given again in meters, not in kilometers. It's given in meters as 6,38 times 10 to the 6. Okay, so we know this distance, we just don't know the distance above the Earth. Okay, but remember the formula encompasses all of this. The formula encompasses, will I be able to turn this? Yes, I can make it a bit more straight. Okay, so the formula encompasses the entire distance between the center of the center of the Earth and the center of the satellite as well. That's what the formula encompasses for. So basically, we need to understand that the formula, we are going to use 6,38 times 10 to the 6 plus x. Okay, now there's two ways for us to solve this, right? The one way, which is I think maybe the more simpler way, is to actually get that value, r squared. Why? Because we know F. In this case, F is known. We know that the force that they exert on each other is 1842,50. So since we know F, we can get the total distance between their centers. Okay, so let's do that. So what I can do is I can take R over, it's going to become 1842 times 50 times R squared is equal to this. Okay, now I can leave R squared alone. And essentially it becomes R squared is equal to all of this, okay, divided by this. Okay, then furthermore, I can square root it. And I get R as, sure, please, can I get someone to double check this with me? I am getting a distance of 6 million, listen properly, 597 million, 982 billion, 0.80. I'm getting a distance, and this is in meters, eh? Okay. Yes. Okay. Perfect. 656 times 10 rooted 6. Okay. Perfect. Right. So now we need to remember what we have calculated is actually the entire blue distance. I don't know if blue is the best color. I don't know what is the best color to use here, to be honest. Let's use blue. This entire distance is 657 6.99982 meters. And 6579982 meters comprises of 6.38 times 10 to the 6 and x. So basically the two of them, 6.38 times 10 to the 6 plus x should give me 6,579,982.80. So it's basically a simplification. I'm going to say x is equal to this huge number. Again, you can probably round it off with scientific notation. It's fine. Let's just take everything. This is equal to minus 6.38 times 10 to the 6. I'm getting 199,982.80 meters. Okay, if you guys are getting the same, that's fine. I'll confirm later on with the memo if that's correct. Unfortunately, I don't have the memo in front of me right now. But yes, that's what we calculated. Okay, let's do this question. Write down Newton's law of universal gravitation in words. Lol. An object weighing 140 newtons on the surface of Earth is moved to a position which is 6.7 times 10 to the 6 meters above the surface of the Earth. Calculate the percentage by which its weight will change. That's an interesting question. So, firstly, we need to calculate its new weight. This is the wrong question. Sorry, I wanted to do this question. Okay, a 200 kg rock, okay, lies on the surface of a planet. Okay, just forget about that question. We'll do this question. A 200 kilogram rock lies on the surface of a planet. The acceleration due to gravity on the surface of this planet is 6 meters per second to the -2. Calculate the mass of the planet if its radius is 700 kilometers. Okay, so we have information about certain things. Okay. Okay, so since we know its gravitational acceleration due to its gravity, we know the radius of the planet in kilometers. Okay, we can utilize the other formula. G is equal to G, big G, times M divided by R squared, or D squared. In this one, it's written as D squared. So its acceleration is 6. G is 6.67 times 10 to the -11. Mass of the planet divided by its radius squared. Remember, convert it to meters. So 700 times 10 to the 3 squared. So now when I manipulate it, I get 6 times 700 to the 3 squared divided by 6.67 times 10 to the -11 is equal to big M, which is the mass of the planet. Let's see if this is correct. 6 times 700 times 10 to the 3 squared divided by 6.67 times 10 to the -11. I'm getting the mass of the planet as 4.41 times 10 to the 22. It's going to be in kilograms. I'm going to double check if that is the correct answer. Okay, correct. So that's one way of doing it. Okay, is utilizing that. Now, the reason I say that we mostly use the other formula is because even in cases like this, you can use the other formula. How can you do that? You might ask, F is equal to G times M1 times M2 divided by distance squared, or R squared. Okay, now we can use this because this is the mass of the planet, right? And then this is, what is this, a rock? This is mass of the rock. Okay, G is a constant, that's that. And this is, F is the force that they exert on each other. So we can use it because it has mass of the planet. Now let us substitute, right? So G is 6,67 times 10 to the negative 11. Mass of the rock, which is why they give it to us. We didn't use it in that formula. Mass of the rock is 200 kg. Mass of the planet is unknown. The distance between their centers, because it lies on the surface of the planet, the distance between their centers would be the radius of the planet. Okay, it makes sense. How many decimals do you round off? 2. You want to keep it to 2. Unless you're doing chemistry, unless you're doing stoichiometry. In those cases, I would recommend 5 decimal places, 4 to 5 decimal places. And in finance, okay, I would not recommend rounding off. In fact, you shouldn't round off. Okay, we'll note it when we do those respective sections, but I can tell you off the top of my head now, generally 2 decimal places, stoichiometry, anything in chemistry, 4 to 5 decimal places. In finance, do not round off, write every single decimal. So that's why the better you become in finance, the better you become at algebra and rearranging the equation, the easier your questions are going to be. Because if you are not good at rearranging the equation, you are calculating every single thing separately, and then you have a bunch of decimals. If you round off in finance, your answer changes a lot. Okay, so let's continue. So therefore, since the rock lies on the surface of the planet, okay, okay, let's just do a little diagram, because why not? That's going to be an egg. And the Earth is an egg, to be fair. I don't think it's such an egg, but let's just do a circle. And we have a rock on the surface. Sure, it's a big rock. Whatever, okay? So in this case, what is the distance between their centers? You just consider it as the radius of the Earth. Okay, so yes, like I said, so in this case, what we're going to be substituting, simply 700 times 10 to the 3, because we convert it to meters and we square it. Now, since the mass is unknown, right, we have to have a value for force, because we're going to have 2 unknowns, right? We have to have a value for force, okay, meaning the force that the rock exerts on the planet, it's not Earth, okay, or the force that the planet exerts onto the rock. Okay, now in that case, it's not explicitly given to us. They don't tell you, okay, this is the force. However, we do have the gravitational acceleration on that planet. Since we do have the gravitational acceleration on that planet, we could utilize the formula for Fg, because remember I told you that this F could actually be seen as Fg, simply because that force represents the force that 2 objects exert on each other. So sometimes it could be Earth and an object. So what is Fg? Fg is the force that the planet exerts on the object, or the object exerts on the planet. That's what exactly what Fg is. So Fg, remember, is m times g. The mass of this object is 200 kilograms, and the gravitational acceleration is 6. So this is how I could solve it utilizing the other formula. Right, when I do a bunch of algebra, you basically take that over as multiplication, take these over as division. Okay, we get 4,41 times 10 to the 22. This is in kgs. So how close is our answer? It's exactly the same. We get the exact same answer using both formulas. Okay, so okay, cool. I have a feeling that many people struggle with algebra in this case. Okay, so that's it. Let's end it there, right? Unfortunately, we won't do an equilibrium question. We will do that next week. We'll continue organic. Just to round up again, how many of you have started organic? I know some of you are done and starting like next term's work. But you all need to chill. Wait, you guys, sorry, this is grade 11. Organic doesn't exist in your syllabus. Electrostatics. How many of you guys have started electrostatics? Sorry. Guys are probably so lost. You guys do the same things as grade 12s, man. It's confusing. Actually, we're quite on par. You guys are like most on par, if you like. Most of you probably started electrostatics already. We're done with electrostatics. Yeah, you see, now you get those people that are done with electrostatics. They're a bit too fast. And they probably started electromagnetism and maybe electric circuits already. Writing on Tuesday. Starting this week. Haven't even started. Okay, it's fine if you haven't started. It's, I guess, the school you go to. Okay, so it's fine. If you have a question, please put it in the chat or in Q&A. Q&A is also anonymous if you'd like to, for the person that has their hand raised. Okay. Okay, perfect. So yeah, what we'll do is we'll try and let's see how it goes. I don't know if you guys really want to do, you guys can practice this question. Maybe I'll do this question in the extra session. It's a bit of a weird, hard question. You can try it on your own and see how it goes. It's like a level 700 question. It's not so bad, but it's just tricky, right? Could you give an activity on this? I'll try. I would definitely recommend doing past papers. So just going to a past paper. Thank you for that question. I appreciate that question. Just going to a past paper and just going to a past paper website and doing as many past papers as you can in the time that you have. That's what I would recommend. What was I gonna say? Okay, yeah, so cool. So next week, do you guys want to do equilibrium? Okay, equilibrium question. How many of you are struggling with equilibrium questions? I'm gonna get to your question now. How many of you would like to do equilibrium because you are struggling with equilibrium? One person, that's enough to do one. What website must use for past papers? I would recommend testpapers.com or testpapers.co.za. That's what I used. It's called testpapers.co.za. You navigate there, you find grade 11 physics. Okay, cool. Don't worry, we will go through an equilibrium question. We're done with this for now, right? Go practice some questions, see if you have come across anything different, and if you're struggling with it, let me know. Okay, and then you can try this question if you'd like. And then next week, we will probably do an equilibrium question, and then we'll start electrostatics. Okay, that's a big topic. So we'll try and get that done. Why was 700? By the way, electrostatics, grade 11 and grade 12 is like exactly the same. It's just that grade 12 questions can get a bit more harder. So there's an app called Past Papers. It has past papers for all subjects. You could use that as well. There's also a WhatsApp chat bot thing, which you could request for past papers. You could use that as well. So someone asked, why was 700 multiplied by 10 to the 3? Okay, so 700 was given in kilometers. Sorry, I should have maybe done both methods. So 700 was given in kilometers. Okay, guys, please don't be scared to ask questions like, this is not school. Okay, I'm not going to shout you for asking a question, even if it's dumb. Like, there's a reason you're coming for additional tuition after school to clarify all those things that you didn't learn in school. If you're going to be shy or if you're going to refrain from asking questions in tuition, it defeats the purpose of tuition. Okay, so even if it's a dumb question, there's literally a Q&A section that has an anonymous feature where I won't even be able to tell who asked the question, so it doesn't matter. Okay, and the chances you have a question, the chances that someone else has that same question is quite high. Okay, so please don't be afraid to ask questions. Okay, so yeah, so why was 700 multiplied by 10 to the 3? So 700 is in kilometers. We need to convert it to meters. So there's two ways of doing it. So to convert it, you have to multiply it by 1,000. So to go from kilometers to meters, you have to multiply it by 1,000. To go from meters to kilometers, you have to divide by 1,000. Okay. Another way of writing multiply by 1,000 is times 10 to the 3. So I'm basically multiplying 700 by 1,000 to get it to meters. Okay, I hope that makes sense and that answers your question. Okay, I'll leave it open for a few minutes just to see if you guys have any other questions. If not, it's fine. You're free to leave. Okay, actually, before you leave, for those of you who are still here, I don't know if I told you this, but I uploaded a document in your Google Drive. You'll find it there. That basically shows the topics we'll be covering in which term. It's according to the government syllabus and the order in which we'll cover it. So many of you have requested for timetables. Unfortunately, I can't give you a timetable just because it's difficult to allocate how long it's going to take for each topic to complete, but at least that document you can use, that PDF you can use to see which topic we're going to cover next. And if there's a certain topic you want to cover, you can see when it will be covered. Okay, cool. So if there's no questions, then we can end it, but I'll give you guys 1 minute. I have a question, actually, a very, very important question. Who do you guys have for Manchester United versus Liverpool? For those of you who are soccer fans. Since nobody's asking questions. Liverpool. The grade 11 class is full of Liverpool fans, eh? Okay, interesting, interesting. We'll see, we'll see. Arsenal. God damn it. These Arsenal fans, they're so entitled. Like, they didn't ask you, bro. No, I'm joking, I'm joking. Rather you guys than City any day. Okay, cool. So let's end it there. I hope you guys have a good week. All the best at school. I will see you guys next week, same time. Good luck to all of you guys who are writing in this week. And then sorry that we couldn't cover everything before your test, but from next week, hopefully once we start doing the final topic for term 1, then those who are writing afterwards will be fully prepared for that test.